Hello everyone, good morning, good afternoon, good evening to all. Dear authors and invited guests, welcome to technical session 6C. I am Riddhi Gohil, moderator of this session. On behalf of Global Knowledge Research Foundation, it is my great pleasure due to the 6th World Conference on Smart Trend in System Security and Sustainability through Zoom. I hope you will enjoy the knowledgeable and interactive session throughout the day. There is a special note for the all presenter. You will be given a 12 minutes for your presentation and 3 minutes for question answer. And on 7 minutes, I will raise a gentle reminder to conclude your presentation. And there is another request to all. Please stay connected with us until the closing remark. And if you have any query and update, please let me know in the chat box. So, just before we get started, I would like to invite to all, introduction to all, Professor Bal Vidya. Yes, hello, sir.
Hi, hello everyone. I'm looking forward to the various talks. And I think we have 7 talks this afternoon. And the first talk is on predicting the workload in depth collection to improve efficiency of manpower planning. And this talk is by Ponipal Chiwuksek. I'm not sure whether he's there. So over to you.
Yes, sir. So I would, Professor Balvidya is the director of the Center of the Communication Technology Research Group. And his research is in the area of wireless, microwave wireless communication, encompassing 5G mobile phones to satellite technology. Professor Balvidya graduated with the BSc honor in Communication Engineering at MPhil from Leeds University, UK. Prior to this, he was a research and development electronics engineer in the future product department at the Teledyne Defense and at the PYE TVT Philips in the Cambridge. So let's start with our first presenter. Our first presenter is Pon Pimol, and she is going present her title Predicting the Workload in Debt Collection to Improve the Efficiency of Main Power Planning. She is absent, so we moving our next presenter. The next presenter is Minglena, and paper title is a model for the organization of cyber physical production system.
Hello.
Hello, ma'am.
Yeah. This is my presentation.
The research into various literary sources points out that the definition of the concept of cyber-physical production system is not unambiguous to date. In this article, the following unresolved and debating issues in research literature can be drawn. The nature and specific characteristics of the cyber-physical production system have not been studied in sufficient depth. There is no analysis made of the similarities and differences between the concepts production system, cyber-physical system, and cyber-physical production system. The subsystems and the structure of a cyber-physical production system have not been studied in depth. There are no written research works on this topic concerning restructuring of the real-life production system into a cyber-physical production system. It is not clear whether the effects and the surplus value of cyber production. There is no unequivocal opinion concerning what kind of social disturbances will result from the mass restructuring of the real-life production system into a cyber-physical production system. All that requires that the object of study and analysis in the present article should be the main principles of the cyber production organization and the subject of study, generating a model for the organization of a cyber-physical production system. The article is aimed at presenting a summarized model for the organizational order of a cyber-physical production system together with the typical for its organizational structure relations and dependencies. The tasks of the scientific research are critical literary review of basic concepts related to the topic, analysis of the structure of the cyber-physical production system, synthesis of a model for the organization of a cyber-physical production system. The methodology of the research has 3 steps. The first step is defining the concept production system. 3 main definitions for a production system prevailing in research literature. Production as production system. Production system as a part of an enterprise. Production organization as a production system. For the purposes of the present article, production system shall mean a unity of interrelated and mutually determined subsystems, methodology, and toolset, which, on the basis of production process automation, objectivize the nature of the production operations in view of achieving the strategic organizational goals. In structural respect, the production system is based on the principles of systematic approach and consists mainly of 2 subsystems, managing and managed, transforming. The fundamentals of the managing subsystem are the main management functions, and it includes in its structure the subsystems for planning, for forecasting, for organizing, and for controlling. The managed subsystem is related to the transformational process and turning resources into finished products, where it is most often structured into production, servicing subsystems. In spite of the emergence of the term cyber production as early as at the beginning of 21st century, even until today, there is no consensus in science in respect to the definition of the concept cyber-physical production system. That requires focusing the research on further specifying the definition of that concept and synthesizing its major characteristics, which are essentially different from concepts such as production system and cyber-physical system. The second step of the methodology is specifying the definition of the concept cyber-physical production system. The synthesis of the definition shows that the cyber-physical production system is a digital, virtual, and physical production model, connecting the real-life production process and its informational flow with the simulated, identical to the real-life one, virtual production replica model, integrating an information base, analysis of large bulks of data, artificial intelligence, blockchain networks, strategic and production management, which is also planning, organizing, coordinating, and controlling the work of machines, facilities, technologies, sensor devices, robots, production capacities, representing an integral part of real-life production. Analysis of the structure of a cyber-physical production system is the third step of the methodology. The cyber-physical system consists of a 6-level architecture. A production system, consisting of its 2 main subsystems, transforming and managing ones, where the physical production process takes place in a particular temporal and spatial aspect. An intelligent sensor system, designated for gathering data from the real-life production environment through sensors, controlling devices, technologies, management systems, which through the Internet of Things maintain the connection both with the real-life physical environment and with the virtual one through the relation sensor-device technology, management system, server. An information system, where the machine signals gathered by the intelligent sensor system are transformed into semantically meaningful information, while the emphasis in that system is on the self-improvement of the intelligent sensor technologies, which acquire the primary data and turn it into a cognitive information resource, which they supply to the next higher architectural level of the cyber-physical production system. A cyber system operating as a central information center, consisting of a network of cyber devices, which store a large information bulk for different periods of time and with different situational variables, which they analyze through specific, program set in them methodologies, algorithms, models, and tools in view of upgrading the primary information with analytical one, by applying frames and artificial intelligence, and generating on this basis alternative options for choosing strategic and operational steps from the cyber-physical production system. A smart system generating in-depth knowledge about the physical production system based on expert systems, whereby a certain decision is analyzed and informationally provided on the basis of the individual primary information gathered by the intelligent sensor system and turned into semantically meaningful one by the information system and the registered options for choice through comparative analytical activities, events in the cyber system of the cyber physical production system. A managing and feedback system, which implements the solution chosen by the smart system and configures the feedback from the cyberspace to the physical production space, while, at the same time, implements a wide range of controlling tools in view of the self-improvement, self-upgrading, and self-configuring of the cyber physical production system with another similar version of a scenario. There are no papers elaborated in research literature to date concerning the organizational modeling of a cyber-physical production system. The present research is an attempt not only to generate the structure of a cyber-physical production system, but also to define the resources which are necessary for each of its structural elements, toolset, technologies, hardware, and software. On this basis, the production system is the place in space where the elemental and provisional production factors combine physically in a specific temporal aspect. Elements of the production system are the production resources. A core structural element of the production system are the production capacities. The intelligent sensor system is a network of sensors, smart detectors, and systems which gather information about the work of the production system. The information system transforms the data received through the intelligent sensor system from the production system and converts them into information recognizable for the cyber devices. The cyber system is a network of cyber devices which carry out certain analyses in view of creating alternative options for strategic and operational choice in the behavior of the cyber physical production system. The smart system of a cyber-physical production system integrates the added value of the expert systems, which are computer programs presenting knowledge and making logical conclusions on the basis of available information from a certain field in view of solving typical tasks from that field or getting appropriate advice. The hybrid artificial neural network fills in content and functional aspect, the man-aging, and feedback system. The elaborated model for the organization of a cyber-physical production system contributes to the transition from machine-based decision-making to a decision based on evidence and experience. The model leads to overcoming the bottlenecks in the production process at the stage before they actually occur. At the same time, modeling the organization of a cyber-physical production system contributes through its network structure and data-rich environment to the sustainable transition from conventional machine learning to learning on the basis of artificial intelligence and smart machine management.
That was my presentation.
Yeah, thank you. Such a nice presentation. I request to Mr. Balavikri, Professor, please come up with your queries.
Hi, this was a very interesting presentation, Magdalena. Did you have any system in mind when you were doing your modeling?
Yes, I have one production system. This production system must upgrade or restructuring to one cyber physical system.
And did your model, was it accurate in terms of modeling the system?
May I repeat your question, please?
Yeah, when you modeled the system, was it a very good representation of it? How accurate was it?
It was very quiet.
That's very good. Thank you so much. Very interesting talk. I really enjoyed it.
Thank you.
Yeah, so we are moving our next presenter. Our next presenter is going, paper title is Infrastructure and Computation in a Smart City as an e-government contemporary competence. And I think he is an upset. So we are moving our next presenter. Our next presenter is Martha, and paper title is Optimized Hybrid Multi-Criterion Decision Methodology for Wireless Sensor Network.
Okay. Thank you for attending my presentation. I will talk to you about the optimized hybrid multi-criteria decision methodology for wireless sensor networks. The agenda for today is I will give you a brief introduction about multi-criteria decision models, definitions, and some classification. And then I will talk about the model description, the two phases that we have from the model description. There are the data set generator and the optimization cycle, and then some conclusions. For the what is the multi-criteria decision methods? The multi-criteria decision methods are approaches designed to the most get or select the most appropriate, in this case, the wireless sensor network technologies, focused on the input parameters and meeting the quality requirements demanded by the client. So for the evaluation criteria that we need to take under consideration, we have the infrastructure factors, regulatory, technical, environmental, economical, and social factors. For the environmental aspects, we need to take, for example, the type of location, if it's plain, if it's mountainous, the weather parameters, flora and fauna. For the infrastructure factors, we need to take under consideration the electrical power, cellular reception, microwave communication, some types of buildings. For the social factors, we need to consider the size of population, financial population of solvency, and other things. For the technical factors, we need to take the data rate, type of data, channel capacity, bandwidth, reliability, flexibility. And for the regulatory parameters, we need to take the spectrum availability and licensing, for example. And for the economical factors, we need to take under consideration the investment, the paybacks, the operational cost, implementation costs, and other things. Okay, the classification. We can classify these multi-criteria decision methods in two big groups. The first one is the weighted methods, and the other one is the comparison methods. For the weighted methods, we have the process. The first part is to identify the goal, then select the criteria and alternatives, assign some weights, and the two last parts are the mathematical calculations and take the final decisions. Some examples of these weighted methods are the AHP, analytical hierarchy process, AMP, analytical network process, Beaker, and parametric model. And for the other one, the comparison methods, the process is similar. We have the first step, it's to identify the goal, then analyze the infrastructure already installed in the locality and also in cities close to the locality. Define the alternatives and compare the alternatives with the with the inputs and get the final decisions. For this one, we have some examples. One is the business canvas and hub structure models based on the multi-criteria decision methods. I know the business canvas model is for business, but there is one model that is related to the multi-criteria decision methods. As you see here, in these two groups, just only opinions, expert opinions, and theoretical values are included on the multi-criteria decision method, but any real value taken from any simulation is not taken under consideration. And the problem is that at the end of in the implementation or in the operation cost, in the operation step, could be problems, probably high cost or quality communication troubles. So this is a problem. So the model description here, we are research on this model. The first step is to identify the goal. And here we are divided our model in two cycles. The first cycle is the dataset generation, and the second one is the optimization cycle. Why the dataset generator? Because on the second cycle, we are using a neural network to try to get the final decision. So the tool for the final user is the second cycle. The first cycle is just to get the data to train the neural network. So this is our first step, our first cycle. The first step is to identify the goal, and we are divided in three levels. The first level is to collect the project parameters, and then evaluate the environmental and technical risk. And we are using, to start the model, we are using the AHP model, the analytical hierarchy process, to compare the theoretical values with the inputs and get the first preliminary selection list. And this list is the input for the level number 2. On the level number 2, we are evaluate just the budget and the implementation and operation cost. And on level 3, we are using a network simulation. We are using NetSim to simulate a real scenario with the input parameters required for the client. And then we need to get the final decision for our outputs on the simulation. We are getting throughput, delay, percentage of lost packet, and the jitter. So this is an analysis for level number 1. So let XI the customer requirement and XJ the technical specification. Here to assign a value, here we are using the SETI rating scale. That is this one that you have in the table. And then at the end, we are following this the AHP model, and we are getting the first list for the first level. Then we have the budget evaluation, and at the end we evaluate the quality of the communication, and we get the final results. This is the second cycle. This is the optimization cycle. It's similar than the previous one. The difference is that here we include on level 1, we include the neural network stage. And as you know, for the neural network, we need to divide the neural network in two steps. The first step of the two phases. The two phases are in the neural network, communication in the file, and then the backhaul. So for the backhaul, to choose or select the backhaul, we are using a deterministic method. For the wireless sensor file, we are using the neural network. And the rest of the levels are exactly the same as the previous one. The comparison between project budget and implementation cost. And at the end, we are evaluating the environmental and technical risk and provide some suggestion for the customer. Here, our inputs at this time are this one, coverage
No, ma'am,
area.
sorry for the interruption. You have only 2 minutes left.
Sorry, I can't understand.
Yes, you only 2 minutes left.
Okay. Okay, on the inputs, we have the coverage area, distance between nodes, and type of data, and the outputs are this one, and we are consider these technologies. For the backhaul, it depends of the distance of this control center, so it's a deterministic method. The conclusions. So the hybrid model is a new selection methodology that it includes several important project parameters taken under consideration to prevent any trouble in the future in the implementation or in the operation part. The components that we need to evaluate are environmental, technical, social, regulatory aspects. So here in this model, we are included real values and also the theoretical values at the same time. The AHP model, also the results can help us as a tool to compare our final results with the AHP model. At this time, we are designing the neural networks. We are trying to get the final result with this one. So this is my presentation. Thank you so much for attending. If you have any question, please let me know.
Hi, Martha. I've got a question for you.
Yeah.
Have you applied your model in a real situation?
At this time, no. We are designing the model. Now I'm designing the neural network. I'm start with the real value for the AHP with the AHP model, but at this time I'm using the AMFIS algorithm to try to get the second cycle of that and simulate everything. The simulations are already done, but I need to design the neural network and train the neural network and try to see what is happening.
Yeah, I've got a follow-up question. Your model is quite sophisticated. It implies that it can access multiple sensors and obviously different sensors, and you can make a selection based on the criteria you've actually in your model. I think if you're applying this model to a real world situation, it's going to be quite challenging to verify. You just need to limit the number of sensors first, and then obviously build on that once you've got the data. But it's a very interesting project. Thank you very much. The presentation is very clear. Thank you.
Okay, thank you.
Yeah, thank you very much. So we are moving on next presenter. And paper title is Infrastructure and Computation in Smart City as an e-government contemporary
Now you can see my presentation, right?
Yes, sir.
Okay, so hello everybody. Our project is a kind of continuation from our last year presentation. So we are international team from 2 countries, from Russian Federation and Republic of Indonesia. So let me just present what we've done for this year. Moscow is one of the smart cities and manifests rapidly upload design technologies, means of communication, new values, and communicative meanings. You can see one of our sites we created. Moscow is our city. Here you can see the number of users. You can see number of problems which been already solved, you know, over 6 million problems. And you know, we have almost 20,000 access points to free unlimited internet. They been installed successfully recently. And you can see here the portal of Moscow Active Citizen. Also here you can see the number of active citizens, active users, number of voting on different topics, and almost, it's incredible, 200 million ideas accepted, you know, for 4 or 5 years, yeah. So Active Citizen platform based on newly created government's online platform. And your best ideas could be implemented here. You can present your idea, then people will vote for this idea or reject it, and then it will be implemented into practice. And besides this, Moscow was one of the first to receive a certificate of successful implementation of international key performance indicators for smart sustainable cities. And about 330 online services made it possible to realize a number of valuable for citizens projects based on people's active social position, like our city, as well as Active Citizen based on newly created government's online platform. And our object of research this year is transportation system of Moscow. The taxi service is in high demand as in each great capital. So we decided to talk about new service opened by us. It's called the Ruli service. Ruli, it means drive. Its media service in the transport complex of the city of Moscow brings some novelty in the e-government contemporary competence. And I have to mention that, you know, we made a comparative analysis with Gojek in Indonesia. Last year I made presentation on this topic. So for now, we talk about project which is called Ruli or Drive. It's a service that allows anyone to rent their car to other people, peer-to-peer. At the same time, only the owner of the car decides to whom and on what conditions he is allowed to rent it. So why is the service interesting for car owners? Just imagine you are in the city center at work and the car is in the parking lot. You don't use a car, but you pay for parking. With the help of Ruli service, which was decided by our team, you can save money and even get additional income from renting a car. This project is so important for the city, and city supports us. The more people use one car, the less cars there are in the city, on the streets. Hence the road network, if unloaded, is unloaded, and there are more free spaces in parking lots. This has a positive effect on the appearance of the city, its workload and ecology. You see here in this pie diagram that personal cars is idle without movement 90%, while operating only 10%. That was the main idea to create this service. So the service package provides installation of special equipment connected with mobile application multi-drive. In this way, over 5 million idle cars will be busy, reducing the traffic overloading in the city, which is of 4.7 million units. In Moscow region, the total number is over 7.7 million vehicles, which is about 13% of the total transportation in Russia. This car is designed, this project and your car designed for sharing with your friends. So a service makes it easy to share your car with friends and your family. Download the application, you can see this on our site, or leave a request and take part in the service testing program. The Safe City and Smart City programs provide mechanisms for creating a comfortable urban environment, including conditions for unloading road and transport infrastructure. In 2020, within the framework of the national project Safe and High Quality Roads, the digitalization and automation of the road transport complex was specified in the regulatory act of the relevant federal executive body. So our project was supported by the government by special decree. And 8 modules and 35 subsystems of the Unified Transport System Management Platform reflect the directions of digitalization and digital transformation of the road transport industry. Its main advantage is the ability to get away from the narrow profile task of building each individual system. So we decided to create just one system for cities with the population over 300,000 people. By providing an information space for public discussion and dissemination of information and opinions, the media plays an important role in establishing feedback with society. So we implement this idea into practice, allowing the authorities to hear the requests of various social groups, analyze and adjust public policy. The digital transport platform was born from the need for cheaper, faster, safer, more efficient transport services. And the project, which was first announced in Moscow, started in 2018, as I mentioned before. This service allows a car enthusiast to rent out his car, earn extra money on it, and the city gets a chance to unload roads to optimize the management of transport infrastructure. Immediately after the launch of the project, we received more than 500 applications from potential tenants. After the launch of closed testing, car owners of the service received more than immediately in 10 minutes 150 applications from potential car owners and 500 applications from potential tenants. And the special package includes, it's very interesting, yeah, installation of special equipment, driving a vehicle without key using the steering wheel's mobile application, registration on multi-drive service for 3 months for that kind of testing. To do this, the owner will need to go through the procedure for connecting the vehicle, send an application to the connection, wait for response, and if the vehicle passes the necessary procedure, the manager will sign up for the installation of special equipment to install this equipment to your car. The car owner come to the technical center on his own or use the free driver service of the early service. Invite friends and relatives to use the contact list in your phone and invite those with whom you are ready to share the vehicle. The tenant, the interest lies in the following: beneficial use of individual terms. The owner can hand over hand over his vehicle to the tenant, just like that. These are more flexible and favorable conditions than rental, just rental. Simply and quickly, the tenant receives a notification about the available vehicles of his friends and chooses the right one. There is no need to pick up the key and meet. The tenant will get access the vehicles through the early mobile application. The comfort is that your friend's vehicle, which has not been used by many people, you know, it's very important under COVID circumstances. Interest for the tenant in providing the opportunity to ride on different vehicles and gain access to unusual models. After a full-fledged launch, Ruli will switch to a subscription model. The car owners will pay monthly for equipment, access to the service.
Sir, you have 2 minutes left for the.
Okay, ma'am. Yes, I'm just almost done. Theoretically, this way can recap the subscription. However, really doesn't plan to promote the development of bike rental when a person buys a car specifically for renting. In this case, I want to add that due to additional services, really will be able to take a commission from partners. But these are long-term plans and prospects. The project is fully funded by e-government, which has no intention of making money on this service. A subscription is needed to cover the cost of equipment, insurance, etc. The city is solving different problem. To activate more than 5 million cars, which stand in one place for 22 hours a day, and to reduce the number of newly purchased cars. At the same time, the service may face problem of users' distrust due to the possibility of surveillance. To connect the car to the relay service, the owner must install special equipment from partners to the department. And the relay service has already received feedback from users who are afraid of surveillance and a leakage of personal data as well. The research is almost finished. The research methodology includes 2 stages, which include a pilot study, which has already been done. The number of vehicles in Moscow is 4.7 million, as I mentioned before. If we add the Moscow region to this number, then the total volume will be 7.7 million vehicles, which is 13% of the whole transportation in Russia. At the second stage, which has been underway for now, an international group of independent experts selected 7 finalists. Among them, Moscow, then Canada, Australia, Vietnam, cities from Brazil. Thanks to the continuous development of urban digital technologies over the past 4 years, Moscow is among the smart cities according to Smart 31, and the second in the top 7 smart communities. And in 2018, it was decided to abandon diesel buses and switch on an environmentally friendly mode of transportation in different spheres. And let me just make my conclusion. The largest revenue from digital services offered on the internet in Russia was obtained by taxi and car sharing companies. So this industry has been under development and shows some good prospects. The digital services industry plays a significant role in the development of e-commerce in Russia. The 5th largest city by smartphone users worldwide, Russia offers a wide range of opportunities for business to reach consumers via internet. And if you look at this graph, you can see, revenue of e-services like dating services, event tickets, online food delivery, and you can see the prospects of this service. A study of media service showed that attracting an audience is the main problem for this service. Since it's necessary to change the attitude towards a personal car to convince car owners and tenants that the relay service helps to save time, since it is possible to rent a car at any time and return it to anywhere. Thank you so much for your attention, ma'am. Thank you so much. This is our international team from Indonesia and Russia.
Yeah, thank you so much.
Thank you so much, ma'am.
Yeah, have you any queries, sir?
Yeah, Valerie, very interesting talk. Amazing things that you're doing. 2 questions. The first one is, you've created a platform where you encourage people to put forward their ideas and you vote on the ideas, and then you said that they implement the ideas. So it's really, people just want to see whether the ideas are feasible. If they're feasible, right, a vote, then they obviously go ahead and implement it. Very good idea. In fact, so if that's the case, then one people steal their ideas and other people then implement them. Would that be a negative thing, you reckon? Like if I have a fantastic idea, I'm not going to propagate it to them.
Yeah, I see. I do agree with you, because as you mentioned, and I also was talking about that in my presentation, that, there are, of course, we are facing some problems, some limitations, but the problem is actually the main idea, the key sales point, that we share our car with our friends, people who you believe in, with good reputation. Because really, you are right. There are many problems which could be caused by, if you just give your car to somebody who is not in your list, at least on your iPhone. So you're sharing with your friends, with close friends. The main idea is that you can trust to those people, and you can, if you're driving for let's say diesel car, you can change for hybrid car or something like this. So I think for green ecology, this topic is very important, because in our city we changed many transportation, like public transportation, like river trams, river boats. They all are using green energy for now. Yeah. We're not talking too much about this, but we're trying to implement this idea into practice. So our small project found very good response from the government, because it's part of government competence as well. Yeah, and I think for any capital, this is of high importance. I think so.
I think you've already mentioned this.
Just a minute. Next year is supposed to give you full results of this presentation. As I mentioned, previous year we started this project, we implemented. Next year is supposed to make presentation for everyone with real results and the real scenarios. Yeah, with some figures.
Fantastic. Just one more comment. You did mention
Sure.
about surveillance and how to mitigate surveillance, right? Another thing I showed very quickly was a graph where Rudy was used for delivery very quick. But I saw on the graph that the dating didn't go up. It's mostly delivery of items, goods, and services. But thank you so much. Your presentation is very interesting.
Thank you, sir, for your question. See you next year. Thank you. Bye-bye.
Yeah, thank you, sir. So
Thanks, ma'am.
our next presenter is Minglena, and the paper data is a concept for restructuring the production system into cyber physical production system.
And the presentation.
Synthesizing a concept for restructuring the production systems into cyber-physical production systems is required due to a shortage of scientific research and elaborations under this topic, as well as due to the need of systematization of the available to-date fragmentary definitions, theoretical fundamentals, and practical applied models. Moreover, there is a huge gap in research literature, not only in respect to the definition of the process of restructuring the cyber-physical production systems, but also concerning the qualitative determining of the notion cyber-physical production system. Therefore, the present concept is related to the need of defining the notion restructuring the production systems into cyber-physical production systems, theoretical research of the fundamental restructuring activities, determining the borderlines, element, and scope of restructuring the production systems into cyber-physical production systems. On the background of the defined needs and theoretical filling of the gaps in the scientific doctrine, the concept for the restructuring of the production systems into cyber-physical production systems is based on the analysis of numerous definitions of the notions production system, cyber-physical production system, restructuring, the synthesis of definitions serving the concept, studying and determining the borderlines, components, and functions of the restructuring process, the analysis of the production system elements, which are subject to restructuring to cyber-physical production systems, studying and outlining the typical characteristics of the specific types of restructuring, object of study in the present article are fundamental notions, knowledge, and practices in the field of restructuring the production systems into cyber-physical production systems. Subject of analysis is restructuring the production systems into cyber-physical production systems. The goal of the research work is synthesizing the conceptual fundamentals for restructuring the production systems into cyber-physical production systems. Methodology of the research includes theoretical review of the main concepts under this topic and synthesis of definitions. On the basis of studying the definitions of the notion production system, it can be summarized that the production system is a spatial arrangement of the workplaces in the production process, as well as structuring the production times and the time-based organizational principle. The spatial and temporal principles lay out the organizational forms in the production system, relates the rationality of the economic action with the value obtained at the output, which is higher than the one that is entered at the input. On this basis, the production system is a specific unity of interrelated and interdependent subsystems, methodology, and toolset, which on the basis of automation of the production process, objectivize the nature of the production operations in view of achieving the strategic organizational goals and the operational production assignments. In a structural respect, the production system is based on the principles of the systematic approach and is generally comprised of two subsystems, managing and managed, transforming one. The cyber-physical production system can be defined as a cyber system and a real-life physical system connected with each other in a real-life production environment within a single and integral system. On this basis, the cyber-physical production system is a digital, virtual, and physical production model based on the elemental fundaments of the ecosystems, machine, human, and blockchain networks, connecting the real-life production process and its information flows with a simulated, identical with the real one, virtual production model integrating information basis, analysis and evaluation of large bulks of data, artificial intelligence, the Internet of Things, the Internet of Services, cloud computing, strategic and production management, and a planning, organizing and coordinating one, which controls the work of machines, facilities, technologies, sensor devices, robots, production capacities, representing an integral part of the real-life production. The concept restructuring has been studied in research literature. However, that has been done primarily from the perspective of an organization in general. There is no available definition of the process of restructuring the production systems into cyber-physical production systems. On the background of the studied sources, a well-grounded conclusion can be drawn that restructuring the production systems into cyber-physical production systems is a long-term process focused on a comprehensive and simultaneous fundamental reorganization of production through improvement of old processes and introduction of entirely new process chains, technological upgrading of existing structural elements, or incorporating new architectural levels into the organizational and structural unity of production, further improvement of used work methods, mechanisms, and approaches, or the implementation into the production process of innovative, highly technological tools and methodological, operational, and strategic approaches. Restructuring the production systems into cyber-physical production systems is a radical reorganization, fundamental change, prompted by the development of Industry 4.0 and the penetration into the production process of additive production, additive materials, nanotechnologies, robotics, photonics, micro and nanoelectronics, the information and technological systems, cloud technologies, the Internet of Things, the blockchain networks, mechatronics, and artificial intelligence. The restructuring of the production systems into cyber-physical production systems is a long-term targeted process aimed at synergy, efficiency, and optimality of production, comprising the entire organization and structural and management unity of production as a system. According to some sources, the restructuring with economic entities, applying smart management, is based on the dissipative concept for change, considering the organization and the environment as a single unity, and creates an order of a higher degree. Adopting that definition, a conclusion can be drawn by analogy that the restructuring of the production systems into cyber-physical production systems is also based on the dissipative concept for change, however, on a micro level, production. In that sense, both production and environment should be analyzed as a single systematic dissipative structure, which content is entirely filled with the transformational process and its management. The activities in the production systems, restructuring them into cyber-physical production systems, should be based on a two-way, sustainable and incessant relation between the production process and environment. This requires that the restructuring of the production systems into cyber-physical production systems should maintain the permanent status of dynamic equilibrium between the production and the microfactors, and should be focused on achieving the strategic and operational organizational goals. As a result of studying various theoretical research works, the analysis of definitions, the synthesis of determinations, and the application of analogy as a tool for argumentation, the cognitive nature of restructuring the production systems into cyber-physical production systems can be brought forward. On this basis, it is defined as a planned, comprehensive, long-term, sustainable reforming change of the production process structure, running from the top to the bottom, and determining its fundamental architectural and organizational and management reorganization. It is evident that restructuring the production systems into cyber-physical production systems means a purposefully planned radical structural change on an operational level, however, directly determined and determining the strategic organizational benchmarks, connected in a two-way mode with them in a relational dependence. The reorganizing activities in restructuring the production systems into cyber-physical production systems are aimed at achieving efficiency, optimality, and synergy. They are accompanied by a high risk and should be focused on further improvement of the system of the existing production processes or introduction of entirely new system-bound process production chains, technological transformation of the production structure or upgrading it with innovative and new structural subsystems, modernizing the work methods, mechanisms, and approaches or implementing innovative, highly technological tools. borderlines of restructuring of the production systems into cyber-physical production systems result from the nature of the two concepts of architecture. These borderline issues are the fact that the cyber-physical production systems have two main subsystems, a physical and a cyber one, which are, themselves, also subjected to the principles of a systematic approach and integrate in a systematic unity and interdependence a number of complex relations. The production systems, with their two major subsystems, managing and managed one, are restructured to a subsystem of the cyber-physical production systems and become a part of their physical subsystems, which preserve the autonomy of a part of the structural elements of the real-life production systems. At the same time, the production systems, already as subsystems, become a part of the physical subsystems of the cyber-physical production systems and are involved in relations and dependencies from the subsystems, forming the cyber subsystems of the cyber-physical production system. The elements of restructuring of the production systems into cyber-physical production systems issue from the structure of the two systems. The real-life production subsystem, where the physical production process takes place in a particular temporal and spatial aspect, should be integrated and upgraded with new structural elements, such
Sorry
as
for the interruption. You have 2 minutes left for the presentation, ma'am.
Production environment. A subsystem where the gathered production machine signals are transformed into semantically rationalized information. A subsystem functioning as a central information center of a network of cyber devices, which store a large information bulk. A subsystem based on expert systems, whereby a particular decision is analyzed and informationally supported. A subsystem which implements the chosen decision and configures the feedback from the cyberspace to the physical production system.
Sorry for the
A well-rounded conclusion can be drawn as a result of the present study. The restructuring
I think she has something technical issue. So over we are moving our next presenter. Our next presenter is a Prashant Watts, and the paper title is a deep convolution network based pneumonia identification from theoretic X-ray imagery scan. I think he is also absent. So, sir, can we wait for the 5 minutes for them?
Yes, we can. 5 minutes, yeah.
Yes, sir. We can wait for the 5 minutes. So, after 5 minutes, we are ending our session. So, we are moving toward closing this session.
Great. Thank you so much, Riddhi.
Yes, sir.
We had some really interesting presentations today. Thank you, everyone. The presentations were very informative. I learned a great deal from them, and I'm looking forward to your other papers, other presentations. Thank you so much.
Yeah, sir. So thank you so much. So I sincerely thank our all authors for their great presentation and contribution to this session, and all our participants for being a part of this international conference. I hope this session was informative enough. On behalf of the whole team, thank you for your support in this version and the previous 5th version. We will happy to have you in the 7th version in 2023. So all the presenter would be getting their digital certificates within a 2 or 3 working days. Further, all the papers are already forwarded to the stranger, and the publication will be live within a 6 months. So kindly cooperate with the team of WS4 2022. And I also thank our chair of the session, Professor Bahar Wilde, for chairing. And here is the token of appreciation on behalf of Global Knowledge Research Foundation and the whole team of WS4. Yeah, thank you so much for chairing the session and your valuable presence, sir.
Thank you so much. I really appreciate it. Thank you.
So dear all, I would like to request all, please turn on your camera for the quick snapshot of the virtual conference. Yes, Valerie, if you can possible, please turn on your camera so we can capture a good memory of this virtual conference. No problem. Just start. Thank you so much and stay safe, take care.